When finding an absolute extrema on a closed interval, you need to evaluate the function at the critical points inside the interval and also at the endpoints. Now C is a little different because it's not a closed interval, so in that case we may have to think a little bit differently. Alright, so let's start with A. We start by finding the critical number, which is the place where the derivative is equal to 0. Set the derivative equal to 0 and you get x equals to 4. Evaluate the original function at 4. And in this case it's positive 16 minus 7, which is 9. And then evaluate the function at the endpoints, which is 1 and 5, right? So f of 1. And be careful, it's negative and then 1 squared, so it doesn't include the minus sign when you square, so this is still negative 1. It's very important to know how much the square is being affecting. Right. That's going to be 0. So let's see, 40, 15 minus 7, that's 8. Okay, so among these, what's the maximum? The maximum is 9. 9 is the highest number. So absolute extrema actually is x and y coordinates. It's a point on graph, meaning that need both x and y coordinates. Okay, so the max, absolute max, would be 4, 9, and the absolute min would be, the lowest value is 0 here, so it's 1, 0. Okay, so that's your answer. All right, next question. It's the same kind of question, except that it requires a little bit more care when you differentiate, because it's a product of two functions, right? So when you deal with the product of two functions, you have to use the product rule. X differentiates to 1. And then when you differentiate e to the negative x, you have to use the chain rule. So the derivative, think of this negative x as just x. So that doesn't change because e to the x differentiates to e to the x. But then negative x, which is the inside function, has to be pulled out and differentiated. And that gives you 1 e to the negative x minus x e to the negative x. And you really need to simplify, or else you wouldn't know when this is equal to 0. Okay, so now I need the critical number. In our case, it's when the derivative is equal to 0. And when one or more things multiply to 0, the only way that can happen is when individual things multiply to 0. So either 1 minus x is equal to 0 or e to the negative x is equal to 0. Now this one happens when x is 1, whereas this one, well, the left side is 1 over e to the x, and e to the x is never 0. E to the anything is never 0, actually. This does not exist. Okay. So for no value of x, that can this be equal to 0. So no such solution exists here. So that means x equal to 1 is the only critical number. Now, once you found the critical number, then the next step is to evaluate f at 1 is 1 times e to the negative 1, which is 1 over e. F at 0 is 0 times e to the 0th power, so that's just 0. And f at 3 is 3 times e to the negative 3. So that's equal to 3 over e cubed. Okay. Now, it's helpful to know that the value of e is about 2.7. So this is like 1 over 2.7, but this is 3 over 2.7, 2.7, 2.7. 2.7 is about 3, so you can kind of think of this as 3 and e canceling and leaving you with 1 over e squared. So the value of this number and 1 over e squared is comparable. There won't be that much different. And therefore, we see that this is bigger than this. Okay. Another way to see that, if you're not so satisfied with this explanation, is just to look at f prime of 2. F prime of 2 is 1 minus 2 e to the negative 2, because e to the any power is always positive and this is negative. This is actually less than 0, right? So that means f is decreasing, which means the function goes like this. It's 0 at 0, and at 1 it's 1 over e, but then I don't know what happens, but it definitely is decreasing afterwards. Okay, so it must be going up and then coming down like that. Okay, and that's why I can conclude that this value f of 3 better be smaller than 1 over e because it's decreasing. Okay, so you can either think about one of these two explanations and be convinced, and therefore the absolute max would be happening at 1 comma 1 over e. Remember, it's x and y coordinates. You can't just write down the x coordinate or the y coordinates. You have to put both. Okay, and absolute minimum happens at 0. 0 is the smallest value among these. These are positive, right? So definitely 0 is smaller, so it's 0 comma 0. So that's the answer. Okay, now the challenging one. What to do with this? Well, this one, because it's an open interval, you really need to know the shape of this graph, or else you would have no idea what's going on. Okay. All right. So let's try to think about the shape of this graph. First, you can split this fraction into two, this and this. So that can be written as 3x squared over x plus 2 over x. And the reason I want to do this is to find the derivative easily. You don't have to do this, but then trying to differentiate this will require quotient rule, and it's not very pleasant using the quotient rule. Okay, so alright, so anyways, this is what we do, and then f prime of x would be 3, and then remember 1 over x prime is negative 1 over x, right? And negative 1 over x squared, right? So it's going to be 2 over x squared. That's going to be your derivative. Set that equal to 0. So the critical number would be happening when this is equal to 0. And I don't like fractions, so let's just multiply x squared everywhere. See, if you multiply x squared to all the terms you see, these cancel, and 0 times anything is 0, so you just have 3x squared minus 2 equals 0. 3x squared is 2, and then x squared is 2 over 3, and x is equal to plus or minus square root of 2 over 3. But because we are on this interval, we see that the only critical number that belongs in this interval is when you have square root of 2 over 3. So that's the only critical number. Okay? Alright, but then because we don't have any endpoints to plug in, you really need to know the behavior of the function. And to do that, let's use the first derivative test. So here's radical 2 over 3. the critical number, and let's pick a number slightly less than square root of 2 over 3. Unfortunately, the derivative does not exist at 0. If you plug in 0, it just doesn't exist. So because we're really interested in what happens between 0 to square root of 2 over 3, we have to pick a test point between these two numbers. And 2 over 3 square root, it's less than 1 because 2 over 3 is less than 1. But definitely it should be bigger than 0.1. Okay, so I'll just choose 0.1. Okay, or 1 over 10. So I'm going to choose 1 over 10 as my test point between 0 to square root of 2 over 3. And after square root of 2 over 3 until infinity, which is the right side, I'll just choose 1 as the test point. Okay. Evaluate f prime at 1 over 10, which is 3 minus 2 over 1 over 10 squared is 1 over 100. But division by a fraction is multiplication by its reciprocal, right? So it's 2 times 100 over 1, the reciprocal. And that's 3 minus 200. That's definitely negative. So that's less than 0. Put a minus here. F prime of 1 would be 3 minus 2 over 1 squared, which is 3 minus 2, which is 1. That's positive. This is positive. And that is the sign of f prime, which means f must be decreasing and then increasing. Okay. Furthermore, if you send limit x going to 0 plus for this function, 3x squared plus 2 over x, well, the top, if you plug in 0, it's like 2. If you plug in 0, that's 2, right? On the other hand, if you plug in 0 plus, it's a very small number that's positive. Think like 0.001, 0.000001. And those numbers, if you divide it, this becomes a huge positive number, so that becomes infinity. And infinity is bigger than any number, so for this function, no max exists. Because if infinity is not a number, you can't say infinity is the maximum. If you get an infinity as the largest value, then you say the function doesn't have a maximum, because no matter what number you choose, it still managed to become bigger than that. Okay, and because it goes down and then goes up. Oh, by the way, this actually means that the function has a vertical asymptote at 0, so it goes like that. Okay, and then goes up like that. So this point would be a minimum because it decreased before and increased after. So we know that f of x has absolute minimum at radical 2 over 3, comma, oh, I have to find the value there. Let's see, f of, let me choose a different color so it doesn't get confusing. Okay, so f of square root of 2 over 3 is 3 times square root of 2 over 3 squared plus 2 over square root of 2 over 3. And then this would be 3 times 2 over 3 because square root and square cancel each other. And 3 and 3 cancels, right? And then instead of dividing by square root of 3 to square root of 2 over 3, I'm going to put the reciprocal, multiplication by reciprocal. And that gives you 4 times square root of 3 over 2, okay? Because 2 plus 2 is 4, okay? So that's going to be our y coordinate. All right. So that's the answer. Let's move on to the next question. So here we're given the graph of f prime, and from there we have to figure out the behavior of the original function. It's a warning. these are graphs of f prime. Okay. All right, so let me start with the first one. What is this graph saying? It's saying that f prime is 0 at 0 and 0 at 3. Okay. And between 0 to 3, f prime is positive. After 3, f prime is positive as well. And before 0, f prime is negative. Now, that means the function must be decreasing, increasing, and then increasing. Okay. All right. So if you know this, then we are ready to answer that question. A, find the critical numbers. Well, the critical numbers are where f prime is 0. Okay. When x is, we just noted here, as 0 and 3. When x is 0 and x equals to 3. Those are the critical numbers. Okay. Now, find the x-coordinates of the inflection point. Well, what is an inflection point? That's when f double prime changes sign, right? Because it's talking about the inflection point, unfortunately, we'll have to think about the graph of f double prime. So graph of f double prime. And f double prime is just the derivative of this function, so you just have to figure out when it has a horizontal asymptote and a horizontal tangent line. So at 1 and at 3, f double prime is 0, right? And also, it's increasing beforehand, so f double prime is positive before 1. F prime is decreasing, so its derivative must be negative. And f prime is increasing afterwards, so it must be positive. Okay. Now that we have figured out when f double prime is 0 and f double prime is positive or negative, that tells us what f does, because if it's a plus, then it's a smiley face, so it's a concave up, and here it's a frowning face, and over here it's smiling again. So we do see that before and after 1 and before after 3, the sign of f double prime does change, and therefore f becomes concave up to concave down, and then concave down to concave up. And therefore, inflection points happen at x equals to 1 and x equals to 3. Okay? All right, and then now back to our critical point. The critical point are 0 and 3. And for 0, we see that the function is decreasing and then increasing again, so it must be a relative minimum. On the other hand, for 3, it's increasing and then increasing again, and therefore it's neither. If something's increasing and then increasing again, it's neither. So this is not an inflection point. It's an inflection point, right? But it's not a relative minimum nor a relative maximum. Okay? All right, so let's do the same thing for G prime. Again, just draw a number line, plot where G prime is 0, and then because the function is above the x-axis, it must be positive. And the function is below the x-axis, it must be negative. And the function is below the x-axis again, it must be negative as well. You have to be very careful here. The graph itself is G prime, so you're not looking at the slope when you're asked what G prime is. You're just thinking about when G prime is above the x-axis or below the x-axis. Okay? And only when we talk about g double prime, we talk about whether it's increasing or decreasing. Well, we need that anyway, so let's talk about g double prime. Okay? So for g double prime, the graph has horizontal tangent line at 0 and 2. And before 0, the graph is decreasing, and therefore its derivative must be negative. Okay? Here, the graph is increasing, therefore the derivative of g prime, which is g double prime, derivative of g prime is g double prime. You know that, right? So between 0 to 2, the g prime is increasing, therefore its derivative g double prime must be positive. And then after 2, g double prime is negative because g prime is decreasing. Okay? And then you have to translate these results to what happens to g. G would be frowning and then smiling and then frowning. Whereas over here, g would be increasing, decreasing, and then decreasing again. Okay? Alright, so with all that given, let's find the critical numbers. Critical numbers are when g prime is 0, g prime of x equals to 0 when x equals to negative 1 and x equals to 2. B, because the concavity does change at 0 and 2, inflection points at x equals to 0 and x equals to 2. And C, as you can see, it's increasing then decreasing, so x equals to negative 1 would be relative maximum because it increased before and decreasing after. So it's like a small hill, top of the hill. Okay, that's what we call relative max. Okay, and then here it's decreasing and then decreasing again. So it's more like it's decreasing and then decreasing again. Okay, and that means you have neither. So x equals to 2 is neither relative max nor relative min. Okay, it's not a relative anything. Okay, relative extrema. It's not a relative extrema. Okay. All right. So now next question. Let's say there's a function whose derivative is this and double derivative is this. Also, it has a vertical asymptote at x equals to negative 3. Determine the intervals on which fx increases, decreases, the intervals on which the function is concave up and down, and x values which the function has maximum, minimum, and inflection. Okay. So when we want to talk about the intervals where it increases or decreases, this is solely about f prime. If f prime is positive, then the function increases. If f prime is negative, the function decreases. And if you want to know the sign of f prime, whether it's positive or negative, first you have to figure out when it's equal to 0. So it's 0 at 1 and 0 at 6. On top of that, you also have to figure out what happens before and after a vertical asymptote. Okay, when the denominator is undefined, that's also a potential point where the sign of f prime might change from positive to negative or negative to positive. Okay, but we know that such a function can never go from positive to negative without going through a vertical asymptote or going through a 0. So if f prime ever changes sign, it must change sign only before and after negative 3, before and after 1, and before and after 6. Which justifies our use of picking test points. We can just pick test points and say, well, here's 0, here's 2, here's 10, and here's negative 10. So use these test points. F prime of negative 10 would be negative 10 minus 6, negative 10 minus 1 over negative 10 plus 3, which is negative 16 times negative 11 over 7. Negative times negative is positive, and dividing by positive, that's positive. So we know that's plus here, okay? And then f prime of 0 would be negative 6 times negative 1 over positive 3. Again, that's positive, okay? Is that right? Just a minute. Something looks a little off. Oh, sorry, this is negative, right? Okay, so this must have been this. Sorry, so this is negative, and this is positive, and then f prime of 2 would be negative 4 times 1 over 5, and that's negative. F prime of 10 would be 10 minus 6 is 4, 10 minus 1 is 9, 10 plus 3 is 13, so that's positive. Okay, so because f prime is negative, positive, negative, positive, we know that the function must be decreasing, then increasing, decreasing, and then increasing, okay? And that allows us to answer increasing and decreasing intervals. So f increases on from negative 3 to 1, and also from 6 to infinity, right? Because after 6 it's increasing. And if you have more than one interval, you should put unions. F decreases on let's see, negative infinity until negative 3, and then also between 1 through 6, so that's a union. So that part is done. The intervals in which the function is concave up and down, we can't do that yet because we need to think about f double prime. And x values where the function has maximum, minimum, and inflection. Okay, actually here is talking about relative maximum, relative minimum. Okay, I should have said it that way. Okay, all right. So let's think about the relative. F has relative maximum at, well, what's maximum? When it goes up and then down, right? So that's x equals to 1. And f has relative minimum at x equals to, for a relative minimum it has to go down and then up, down and then up. So negative 3 and 6 seems to be the answer, but wait, negative 3, you have a vertical asymptote. So the function is not defined here, there. So that means f has relative minimum only at x equals to 6. Okay, because over here the function is not defined. Okay. All right. Now let's talk about this other one, the second derivative. So let's think about the second derivative. The second derivative is 0 at 3, and also negative 9, and also negative 3, right? Okay. So that's second derivative. We again pick test points. Negative 10, negative 6. Let's do negative 6. Okay, negative 6, 0, and then 10. And then again we have to evaluate f double prime of negative 10 is negative 10 plus 9 is negative 1. Negative 10 minus 3 would be negative 13. And the denominator is squared, so we don't care. It's always positive. So this must be positive. Okay, so that must be positive. And then f double prime of negative 6 would be 3 times negative 9, and negative 6 plus 3, that's always positive. So this case will be negative because positive times negative is negative. So negative. f double prime of 0 will be 9 times negative 3 over something squared. So that's negative. And f double prime of 10, which is 19 times 7 over something squared, and that's positive. Okay, so it's negative and then positive. All right, which means for the function, since this is second derivative, it's a smiley face, frowning, frowning, smiley face. Okay, and remember at negative 3 we have a vertical asymptote. Okay, all right, so that allows us to say that f is concave up on, well, it's concave up here and there, so from negative infinity up till negative 9, and also 3 to infinity, just like this. Okay, and then f is concave down on negative 9 to negative 3, and also negative 3 to 3. And then finally, the inflection points are where it changes from concave up to concave down, or concave down to concave up. So f has inflection points at x equals to negative 9, and also x equals to positive 3. Because those are the points where concavity changes.